All right, our last speaker of the day is Dr. Sarah Null. Dr. Null is an assistant professor in the Department of Watershed Sciences here at Utah State University. She received her BA in economics from UCLA and both her master's and PhD in geography at UC Davis. She worked as a postdoctoral scholar at UC Davis's Center for Watershed Sciences for 3 years prior to coming to Utah State University. Her research interests include water resource systems analysis for people and ecosystems, climate change impacts and adaptations for water resources, stream temperature modeling and monitoring, and improving information sharing between policymakers, water managers, and researchers. Please join me in welcoming Dr. Sarah Null.
Okay. Awesome. Looks like it's working. Okay, finally we get to talk about water some more. I know you've all been waiting. Okay, so I think we've seen this kind of slide. I just wanted to start us off remembering that temperatures are warming across certainly the western U.S. Up here, this is a kind of a middle-of-the-road emission scenario. Thank you. Middle-of-the-road emission scenario. Precipitation is much more uncertain, though, and so the Pacific Northwest is supposed to become wetter, the Southwest is supposed to become drier, and the Intermountain West is kind of in between with a lot of uncertainty and a good deal of hydrologic variability also. So just as a quick background, kind of thinking about some of the changes between climate change and hydrologic variability, as the air temperatures increase, evaporation also increases. That means the water holding capacity of the atmosphere increases and atmospheric moisture increase. So that part's just physics. Kind of I think about it as temperature increases, relative humidity decreases. What that means is that we expect intensification of the hydrologic cycle. So we expect more very dry years and more very wet years, or kind of a flattening of a probability curve with more points on either side or on either extreme. So today I'm going to be tying a bunch of kind of the topics of the conference together to talk about climate change, disturbance, restoration, and of course water management. So I want to look at how do we manage water with climate change, and so I mean that for people, so I'm going to look at both agriculture and urban uses and then ecosystems also. We're going to look a little bit at water infrastructure, so dams and conveyance like I've shown here. And then just keep in the back of your mind that although I'm mostly talking about climate change and impacts to water management, there are other things changing. So we also care about water reliability with population growth and land use change, and I'm not really talking about those things today. I'm going to be talking a lot about water rights, and this came up earlier today, so just if you're not one of those people who think about water rights every day, as a little refresher, water rights are designed to promote stability, and so we can quantify water reliability, and also so states or governments or even individual farmers can think about infrastructure and technology and maybe invest in some technology. So in the West, we use prior appropriation or appropriative water rights, and that means first in right, first in time, or it's basically a seniority system. So the most senior water right holder will get every drop of water before the next junior water right holder gets any water. They're very common in the western U.S. In the eastern U.S., we use riparian water rights, which means shortages are shared. Those can be problematic where you have lots of droughts because shortages are shared, it can maybe not keep anybody whole. Everyone can take a hit, and maybe nobody's crops grow or no cities get quite enough. And so economically, they can be a little bit more problematic where there's a good amount of drought. So I'm going to be talking about two systems today having specifically to do with water rights and water management. First, we're going to look at climate change effects on season-dependent water rights. I'm using the Tuolumne River in California as a case study, and the reason I'm using that is it's a great representative basin that snowmelt-dominated water supply to a large urban area. And that's important because about 1/6 of the world is dependent on snowmelt-dominated systems, including the Wasatch Front here. It has all three big users, so agriculture, urban areas, and in the environment, and water rights are really simple there. So here in Cache Valley, we have 50 different water districts. There's only 2 in the Tuolumne, so it's just a nice, simple representative basin for us to use. There are lots of places that have season-dependent water rights, and so I want to kind of challenge the conventional idea that shortages are always given to the most junior water right. So we'll take a look at that. And then we're going to follow up on looking at water right purchases or water purchases as a river restoration approach. And we'll look at a system in Nevada and kind of use some parallels to the Great Salt Lake. Okay, so here's the Tuolumne River Basin. It's in central California. So it flows off the west slope of the Sierra Nevada. If you've ever gone to Yosemite and you went to Tuolumne Meadows, you are in the Tuolumne Watershed. If you went to Yosemite Valley, that's down here, you are in the Merced. So the river, Tuolumne River, flows westward, meets the San Joaquin River, flows northward, and out through the Bay Delta. We're just looking at the Tuolumne Basin right in here. Okay, so how are water rights allocated in this basin? They're really simple, as I said. So agricultural users have the most senior water rights. That's common throughout the West, and it just is indicative of how the West was settled. So water rights are usually about 2,000 acre-feet, except for the spring runoff time when they increase. So water rights for this most senior water users increase mid-April through mid-June to really kind of collect a lot of that snowmelt runoff. So this is how it might look, that water right allocation this is a wet year, water year 2011. So the part in dark green here is allocated to agriculture. The rest, any excessive water, is allocated to urban areas. In this case, San Francisco and the Bay Area. This is a dry year. Notice really, really different, right? So all of the water goes to agriculture, no water goes to urban water supply. So whenever you see something like this, you know that there's a lot of infrastructure in this basin. And again, that's representative of the West, where we have large dams and lots of conveyance, really in almost all of our basins. So here in the Tuolumne watershed, everything that's kind of purple is part of the Hetchy system. So Hetchy reservoirs up here. There's an aqueduct that brings water to San Francisco and the Bay Area. Everything in brown is other infrastructure, mostly owned by the state or federal government. All the triangles are dams, all the lines are conveyance. There's two dams I'm going to talk more about. The first is Hetchy Reservoir. If this sounds familiar to you, that's because it's very famous as a reservoir that John Muir kind of famously fought and said, should we have a reservoir in a national park? It was built there, it's still there today. It's a medium-sized reservoir, it's about 360,000 acre-feet. And the new Don Pedro Dam is right in here. So just downstream on the Tuolumne River. This is owned and operated by irrigation districts. It's a large dam, 2 million acre-feet. It's the 6th tallest dam in the United States. So again, really representative of Western water management. Okay, so we've talked about agricultural water rights and urban water rights. So now let's talk about environmental water rights. Not all basins have environmental water rights, but it's increasing. So here in the Tuolumne River, environmental water rights are allocated as part of a FERC hydropower relicensing agreement or part of a settlement. They're for steelhead and Chinook salmon habitat downstream of Don Pedro, that really large reservoir. They're allocated based on water year type. So if you look at this figure, this is by month, and you have water year types with the wettest years in the darkest blue, kind of moving to like pinkish or tan colors as we get dry. And this is one of my favorite things about water year types. As we get drier and drier years, we keep adding kind of adjectives on here. So we go from dry to critical / dry to critically dry to below critically dry. Sometimes I'm seeing extremely critically dry, so we just kind of keep adding more classes on. The above normal and wet historically was about half of the year. And the idea is that in the really dry years, there would be minimum flows. There's always an April pulse flow to cue fish to migrate. In the very dry years, there'd just be minimum flows, and those wet years would happen and provide the hydrologic variability that systems need. So I'll come back to that idea later. Because the environmental water rights are mandated as part of a hydropower relicensing, they de facto get priority. So how this looks in reality, the water right priorities is environmental flows get priority, then agricultural water users, then third urban water users. Environmental flow priority can vary. Sometimes they're last, sometimes they're first, just depending on how they're set up. Okay, so I modeled this using CMIP5 hydroclimate data. So I wanted to model this to just look at, okay, what's going to happen in the future with water rights, and how is water allocated, and who gets the shortages when shortages exist. So I took 16 GCMs, or climate models. They were downscaled as part of CMIP to 1/8 degree. They were run through VIC, which is a hydrologic model, and then this was a really easy study. I just looked at the runoff or the streamflow. I did this on a monthly time step for 150 years. I broke that into 3 periods, so 1950 to 2000 is the historical period. The next period, 2001 to about 2050, is kind of the near term, and then the far term towards the end of the century. So before we get into the results, let's just look at how climate change is anticipated to change in this particular basin. So on this figure, I have air temperature here on the left, precipitation here on the right, and again, this is straight from climate models. The black dark line is modeled historical period, so you can see some interannual variability. I have some shading if you can see it. That's all the variability from different climate models. And then I have the average of 4 emission scenarios. So emission scenarios basically say kind of human uncertainty. So that's how are we going to respond to climate change? How is human population going to keep increasing? Is greenhouse gases going to keep increasing? Or are we going to come into some equilibrium? So we have an optimistic one where by the end of the century we're in equilibrium, and then we have a very severe emission scenario where by the end of the century greenhouse gases continue to increase. So again, this is kind of human uncertainty. Then you look at precipitation and you see a really different pattern. So again, lots of variability. The shading is all on top of each other, the emission scenarios are on top of each other, and the shading band is really huge in here. So what this tells you is, 1, there's lots of interannual variability, and 2, there's lots of uncertainty with precipitation. But we're pretty confident about air temperature increases. So how does that change water resources and hydroclimate? So changing timing of water, so as air temperature increases in mountain basins like the Wasatch or the Sierra Nevada, where we had snowmelt-dominated systems like this blue line, where we had runoff in the spring, even late spring, April, May, and June. And that's good because in the spring and summer, water is a resource. That's when we want water. As temperature increases, we increasingly move to rainfall-dominated systems, more like this one, where we get most of our runoff in the winter. So January, February, March. That's a problem because water in the winter is a hazard from flooding. We don't want water in the winter. We do want water in the summer. So Snowpack stores water. Climate change will affect that. Model fit, I'll go over this quickly. I just wanted to show you that we looked at model fit. By and large, the models fit very, very well. The modeled data tended to overestimate May streamflow a bit. So all of these peaks, the blue modeled is slightly higher, tended to overestimate streamflow a bit. So this is a best case scenario in terms of water supply. If I were to look at flood protection, it'd probably be a worst case scenario. Okay, so let's start by looking at what happens to streamflow. So in these plots, I have month on the x-axis, streamflow on the y-axis, and then these are emission scenarios, so the most optimistic to the most severe. The lines are my 3 time periods, so the tan one is the end of the century. So looking at this figure, it looks very much like that hydrograph I just showed. So we're moving from historical periods when we got lots of spring runoff to much less runoff in the spring and more runoff in the winter. That makes sense. That's what we would expect. So then how is water allocated? So this is a really similar figure, but in this top part here, I have water to the environment, water to agriculture, and water to urban users. And these are basically ranked by priority that they receive water. So looking at this top one, it mostly looks like there's not a lot of change to environmental water rights. And we'll revisit that because this is the same Y scale, so it's a bit hard to see. Look at agriculture, which is the most senior water right, and I'm going to look over here at the most severe emission scenario because it's the easiest to see the changes. So in this, again, we have less water allocated during the spring runoff time period. The other months are about the same. And then when we look at urban water uses, we have less water in the spring, but much more in the winter. So out of all of these water uses, the only one to ever get more water at a different time period is our most junior water right, is urban users. So this is showing a very similar thing, but I put it in box and whisker plots so we can see the variability a good deal more. So this one, again, environmental water uses, agricultural, urban, and here I have my 3 time periods, so historical, midterm, and far term, so you could see the change. So again, you can look at medians, and these are on log scale now, so we can see change a bit better. So looking at environmental water uses, they're sometimes the same, but in some months from April, May, June, actually all the way through about September, they tend to decrease. But they have the most senior or the highest priority water rights, so what's going on there? So that's driven by many more water years are dry and critically dry and extremely critically dry, and less water years are wet and normal. So that because environmental water rights are defined by water year type, which is stationary, those environmental water uses and allocations are still declining. So then let's look at agricultural water use. Sometimes it's the same, but in the spring runoff periods, towards the end of the century, there's huge reductions. And again, remember these, you never really see the whiskers or points going up to the top because remember any excess water goes to urban users. So basically, agricultural water users get less water towards the end of the century. And then we look at urban users, and here, urban users really get any, they're the most junior water right, they get any excess water. So they have times where they have these really huge flows, but they're certainly not the norm. They have times with almost no flows, so July through December, urban water users get almost no water. In the winter, their water is increasing, and they certainly have a ton of variability. In fact, they have the most variability of any of the water users. So then that's only looking at water allocations, but we know that this basin, like most western basins, has a bunch of reservoirs that we could operate and we can manage water. So what's going on here? So I put these results, this is with historical climate, into a water management model that's a hydroeconomic model. And I'm not going to go too much into the details. If you're interested in it, I can talk to you later. So here I wanted to look, so the Tuolumne River is only one water supply option for farmers. So this is all agricultural users. These are these two in the Tuolumne Basin. This one's also in the Central Valley. And so you can look at where they're getting water from. So this teal is the Tuolumne River, that makes sense. Sometimes farmers might pump groundwater. There's some agricultural reuse in green. These tend to be very efficient agricultural basins. There's not flood irrigation or anything like that. Pretty efficient. Sometimes there's some other rivers that farmers can draw water from. And then so this is my kind of base case conditions. But then because this was in the Tuolumne Basin, people have been chatting about possibly removing Hetchy Reservoir for about 100 years. So I wanted to say, okay, what would happen if you took out this dam? So I did a couple of model runs, and I looked at improving conveyance, and you can see across these there's no big changes. So you could take out a dam, there's really no change to water reliability. Then I did this same thing with climate change run. Now red is scarcity, so red is water demanded that would be paid for but that is not being delivered. And you'll see there's a ton of water scarcity. So what does this mean? This means climate change is limiting systems much, much more than infrastructure or reservoir storage space. This is important in Utah where we're considering building new dams, right? So in these systems, precipitation tends to limit water management. So this is an important thing for us to remember throughout the West. And certainly in Utah, where we should think, are we in 50 years and 100 years, are we going to be limited by precipitation? Or are we going to be limited by water storage? And I say that because we're considering building new dams on the Bear River. So some major findings with this before I go into my next section a bit. The changing timing of runoff may benefit junior water rights, so that's not what people think of. This is when there's season-dependent water rights. There's lots of uncertainty still to those junior water rights holders. And this, I've talked about the Tuolumne, but season-dependent water right holders are very common. So all irrigators will only irrigate for part of the year. The Rio-Grande, the South Platte, there's lots of other systems that have season-dependent water rights. These systems in the West tend to be precipitation limited, so building our way out of problems is a poor solution. Some better solutions are conservation or conjunctive water management, so using groundwater and surface water together, and perhaps more conveyance. So now quickly, I have a couple more minutes. So let's go into looking at water rights for river restoration. And in this, I'm looking at Nevada's Walker River. Again, these are season-dependent water rights, so buying from farmers, keeping water in the river. And this system, I didn't specifically model climate change, but it's been in this really horrible prolonged drought that is, in essence, a proxy for climate change. So here's the Walker River Basin. Flows on the east slope of the Sierra Nevada and into Nevada. So there's two big tributaries, the West Fork, the East Fork, kind of moves around this way. Water flows into the Walker Lake. Walker Lake's a terminal lake just like Great Salt Lake. So the only outlet is through evaporation. The Walker Lake and Walker River are pretty hammered. The stream flows are really low from diversions, from dams, from water regulation. That means stream temperatures are really high because there's very, very little water in the river. With that, dissolved oxygen is very low. So stream temperatures and dissolved oxygen are inverse. So those tend to move inversely. That matters because for the last two rivers, Walker River has no longer reached Walker Lake. There's declining fish populations. This used to be a river for Lahontan cutthroat trout, which is federally threatened species. And here's a quick kind of volume of Walker Lake. I'm going to come back to this with Great Salt Lake. And you can see over the last century and a half, the lake has been declining. As this has happened, salinity has increased because, again, it's a terminal lake. So now cutthroat trout no longer live in the lake. So the restoration ideas for this basin is to buy water from farmers. So this is a water marketing approach. We do water marketing in California and the basin I was just talking about, and in Nevada. Utah's somewhat unique in that we don't do water marketing, so buying and selling water. So the questions here were, can we improve habitat with water purchases? When and where is it most useful? And what happens during these really bad dry years that we've had? And to give you an idea of the dry years, so 2011 was a wet year that we monitored and modeled. It was an El Nino year, about 162% of normal snowpack. Two kind of halfway dry years, 50%. This last year, 2015, was 5% of normal snowpack, so really, really dry. And that's why I say these are the conditions we expect to be more common with climate change. The lake dried up, so this looks like a road. It's actually the river just before Walker Lake, and here's a hydrograph. You can see the river drying up. We monitored it, we modeled it with an hourly hydrodynamic and water quality model. And then we took all of these black lines are diversions. They're scaled for the size of diversions, and essentially we just made them points of non-diversion. So really conceptually easy modeling. Model testing, I'll skip because I'm running out of time. We tested this model. So here we have a longitudinal profile. So when we purchase water to leave in the river, that of course increases stream flow. That's pretty easy. Here we're looking at temperature. This is a longitudinal profile. These are maximum temperatures, this black one, so maximum temperatures, minimum temperatures. This is from upstream, this is downstream. And then these gray lines are water purchases. And you can see that water purchases really reduce the daily maximum. They sometimes increase the minimum, but that we think is less important for species. Here, this kind of funniness is where this tributary comes in with more water, so the lake temperature tends to drop or rise at night. This also, as stream temperature decreases, dissolved oxygen improves. So we think this is a pretty good river restoration option. In 2011, there was no days that stream temperatures exceeded 28. We use 28 because it's the lethal threshold for cutthroat trout. So we took 2012, a nice dry year. We went from over a month of days that were much too warm. With water purchases, this is existing purchases. There's been some, which I'll talk about in just a minute. We can really reduce that a lot. So this is a promising restoration alternative for dry years. However, it's much harder to buy water, of course, in dry years. So the availability of water is the best in the wet years. There have been some purchases made for dry years. This is a promising approach, and I'm really leaving all that legal kind of aspects to other folks working on that. So it's promising, but a bit nuanced because it's hardest to purchase water in the dry years. But about 25 million cubic meters of water have been purchased. Little tiny water purchases don't do much for habitat. So here, Walker River and Walker Lake, the water is being explicitly considered and managed for ecosystems. But here in the Great Salt Lake, that's not the case. So here's an image of the Great Salt Lake with kind of the high, when it's at a high lake level of 4211 feet, versus the last 2 years it's been at 4191. And you can see this footprint of the lake, it's about half of its volume. And there's no, water rights or anything to the Great Salt Lake. Here's a picture of the Bear River Bay. This is Compass Mineral Ponds, evaporation ponds. This is Bear River Bay, completely dry. You could drive a car across it. That was taken last August. And here I just wanted to end with this slide. So I think I have one more after this. So here, this is a really easy one, talking about water management and climate change, to blame all your problems on climate change. And this is one where we shouldn't. So climate change certainly affects the lake level of Great Salt Lake, but we also know that diversions from people, so consumptive water uses that aren't ever returning back to the river, has declined the lake level, we think, by about 11 vertical feet out of that 20. So here at Great Salt Lake, we have a mix of climate and water management that we need to improve. And so a few things to end on. How we adapt to climate change is just as important at looking at the effects of climate change. It can basically minimize or double the effects of climate change. So some potential adaptations, we should think about the water uses we want and manage for those, and that's Utah could really improve on that front. A lot of the regulatory mechanisms that we use are stationary, so water rights, water year types, the Endangered Species Act, managed stream flows, these all tend to be stationary mechanisms and frameworks that we use. So anytime we can increase adaptive management is always a good thing, and then these are complex systems, so expect complexity. And with that, I want to thank my graduate students who did much of this work.
Your study on the removal of a Hetchy dam will have any impact on the decisions that are made about taking that out or not?
I would think it would, because it already has. So it went up based partly on research, it went up for a vote with San Francisco voters in 2012, and it was defeated. It wasn't a vote to take out the dam, it was to continue studying taking out the dam. It's currently in litigation, and I'm working with some of those folks. So yeah, so science is being used. Yep.
So why is Utah the outlier on water market?
I don't know why Utah is the outlier. The question was, why is Utah the outlier on water marketing? And I'm not sure, because water markets are common in Nevada and California, and I believe Arizona. So yeah, where my guess is that will change. Water markets are a great way to reallocate water and to incentivize conservation. So my guess is that I think in some other places water is managed tighter than it is in Utah, and as we manage water more tightly, it'll probably start to become more of a solution.